You can kind of think of it as firstly letting the prior evolve, meaning that I keep iterating over some repeated evidence. I keep updating my Bayesian prior over time. That's probably more intuitive, but with regard to the second one, it's a bit more like maybe more cryptic, what I mean by letting the prior devolve. Essentially, I'm going to do you'll see, it's doing the opposite of what Bayes' rule should be doing. That's kind of where it started, but where it led to was this idea of a dual to Bayes' rule that is, I think, the most exciting part of this particular talk. I've been given an hour, but I'll try to keep it less than an hour. And if you want to clarify anything, if there's anything that you think that would be helpful to clarify, please just stop me at any point. Okay, so the context. So when it comes to Bayes' rule, I think we're all familiar with this particular object. And Bayes' rule is important, right? We think that Bayes' rule is something that occurs in a lot of different fields. It's a very important kind of relation and expression. Okay, just to take note, the notation that I'll use looks a bit more complicated, but the whole point of this way of writing it is really the same thing as above. Is really to emphasize that depending on what prior you invoke here, denoted by gamma, it's going to give you a different kind of retrodiction or a different kind of Bayes rule in that sense, or Bayes map given some forward channel. Okay, so I'll kind of explain this later more, but the point here is to say that, yeah, the Bayes rule is ubiquitous and foundational in many different fields, not just in like physical sciences, but also in social sciences, in computational tasks, and decision theory, and so on and so forth. And I'll just emphasize that this is whether or not where you lie on the philosophy of probability question of whether it's a frequentist approach or a Bayesian approach. The point here is that the rule itself is important. Okay, so when we're not going into like the philosophical aspects of this thing, but the rule itself is something that is crucial in all these fields. And it stands to reason that if the world is quantum, or if the future is quantum, whatever that means, right? Having a quantum analog to Bayes' rule would be a nice thing to have, essentially. That's really the question here. Okay, but there's some trouble. There's trouble for the quantum Bayes' rule. And the main thing is something that we probably immediately anticipate is that quantum theory uses a formalism that is whatever you think makes quantum theory very different from classical theory. That is what needs to be accounted for when we come into the quantum regime with regard to a Bayesian inference. But more concretely, something that's highlighted by Rob and Matthew Leifer in 2013, which is actually quite an important paper in this research program, is that quantum theory's formalism just isn't equipped with the conventions that are analogous to probability theory in kind of a naive sense, right? In classical theory, we have causally neutral joint states that induce our Bayes rule, right? It doesn't matter whether it's space-like or time-like separated correlations. We have it, yeah. We describe it with these things. Now this one denoted by omega. But the point here is that the joint state is what induces our Bayes rule. In quantum theory, we don't have that, right? We don't have this kind of unity and causal neutrality with respect to these correlations. So yeah, so these are the troubles, and that's why there's sort of a quest for the quantum Bayes rule. And there are essentially two broad approaches in this this research program. And one way to think of it is in terms of a direct kind of Bayes map expectations approach, and then the joint state expectations approach. So basically, this one says something like, if classical Bayes has this, then some quantum analog of this thing, the quantum Bayes rule has to have. And likewise, for this joint state expectation, you kind of go backwards one step and start from the joint state thing. So let me just give you some examples of what this might look like in this set. In classical Bayes rule, one thing that is well known is that it has to be quote-unquote consistent. Okay, you can think of these as axiomatic features, that essentially if your prior was correct, like gamma, you thought that this was the case, and it turns out that this was really the case, and you do the retrodiction on thing, then you should be able to recover the fact that you were right about the thing. Another thing will be composability. This one might be a bit more, once I say it, it's going to be obvious, is that the retrodiction of a composition is a composition of a retrodiction with regard and with the prior propagated forward. Basically, if you have a trajectory of retrodictions, you could have just done the retrodiction of the trajectory in that sense. Okay?
Ask you a question. What is E with a hat and we without a hat? And
okay, so the E with the hat and the gamma at the side would be the Bayes map or the retrodiction map of the channel E. Okay. And with respect to the prior gamma. Yeah, okay? Yeah. So I'll kind of explain that again later on. Yeah. Okay, and there's a lot of very nice different papers on this thing. One of my contributions with regard to this work is with respect to dilations and also with respect to understanding certain retrodiction maps in terms of quasi-probabilistic representations so that you can kind of compare it to Bayes' rule in a kind of a matrix. Of course, one is quasi-stochastic and the other one is stochastic, but I kind of compare them side by side. If you're interested in that, I would love to talk about those. But there's also the joint state approach, which, as I mentioned, the classical joint, in classical theory, is a joint state that actually induces your Bayes rule. And so what we want in, maybe you can kind of just stop and then first come up with a analog to a joint a description of quantum correlations. And we call this quantum states over time in the literature. And that will induce then your quantum Bayes rule depending on the kind of formalism you use for your joint state. And of course, the 2013 paper by Rob induced a particular map, and this is the PETS also was actually already a very important map, and I think what's very nice about the paper is that it arrived at that map in a very, using this kind of joint state way, and here I'm denoting it as LSP. Later on, I'll drop this this particular superscript because I'm going to really focus on this map because this is the map that really interests me. And but there's also another kind of retrodiction map that was come up with more recently called the Full-Parzignac map that uses a different kind of convention for joint probability distributions. And one of the questions that came up in 2023 is which of these proposals for example, these two, which of these proposals for a quantum joint description satisfies stuff that we would expect from the classical regime. Okay. So just note that the Leifer and Speckens or PETS map is what wins here in this particular, all these different axioms. It has more expected features, but as you might expect, that at least for this paper, it argued that the full Full-Parzignac map wins with respect to the joint state expectations. So, of course, this is not what I wanted to hear, right? Because I would prefer that one map wins both sides. But what I have is one wins the Bayes rule direct situation, and the more indirect joint state one, the other map satisfies the expectations there. One way to kind of resolve this or to understand this is to basically say that maybe what they said about the Leifer and Speckens or PETS map, that it doesn't come from a joint state that is linear or what they call complete, maybe it's not a bug. It's a feature of quantum, the geometry of quantum states, right? Okay, but having said that, I will just say that for today's content, the cell that I'm interested in is here, right? I am interested in adding two new features that our quantum Bayes rule needs to satisfy. And furthermore, I will also argue that the PETS recovery map, this particular map is the map that satisfies, at least numerically, has been shown to satisfy these aspects, and to argue that next time in future work, when we kind of examine other maps in this matter, these new features should also be accounted for in that sense. Okay, so let me just get down to the two new features. And this is really the kind of core part of my talk. And these two new features, I will call it asymptotic frequentism and equated process duals. What on earth does that mean? Let me just give a short description. That the first thing has to do with that Bayes rule coincides with any kind of frequentist method as long as you keep getting the same evidence over and over again in the long run. Basically, if you're Bayesian and you're a frequentist and you keep getting the same evidence over and over again ad infinitum, you should agree eventually. That's really what I'm saying. This one is a lot less obvious. I'll kind of just, for dramatic tension, I won't explain it. Okay, but it has to do with that Bayes should be equipped with a sort of a dual update on the process, okay? And I'll get into that later. Okay, so this is what, yeah, sorry.
Back to the,
yeah.
You said something like, if you're a Bayesian and a frequentist.
Oh.
Those are usually sort of...
Yeah, sorry. If there's a Bayesian and there is a frequentist, they should arrive at the same conclusion if they keep getting the same result over and over again.
And what are they trying to draw a conclusion about? Like, what are they agreeing on ultimately?
So it could be a kind of a hypothesis that gives them some data that over time, basically as a Bayesian, I start with a prior, no? It can actually be a whole bunch of Bayesians, right? But if they keep getting the same evidence over and over again, and if the solution space is identifiable, right, you will eventually converge to the same fact that it's this hypothesis that should be the right one, if you have like an infinite set of data on the thing. And your prior shouldn't matter after that. Yeah.
So, okay, let me just make sure I've understood. Like, usually you would frame that as if I have two agents who are both Bayesians.
Yeah.
They're starting off with different priors. Then, in the limit of getting more and more data, their priors, like their posteriors, will converge.
Yeah.
Is that what you mean?
Yes, and also it's also the case that a frequentist approach, like say a maximum likelihood approach, would also give the same result. Yeah. Given that your data is really very identifiable in that sense. Yeah. I'll give an example of this later with regard to virus self-test. Okay, so this is the two parts of the talk. And let me just kind of first start with talking about Bayesian inference so that we are on the same page. And I kind of already mentioned this, but the prior is important in defining what your kind of a Bayesian reversal or Bayesian inversion of some kind of forward channel is. Your forward channel is not going to be enough for that. You need some kind of marginal to describe it. And this is our notation that we chose. And one way you can think of the reference prior gamma, this Bayesian prior, is our best current guess or background information on the thing. And this particular thing in the denominator is just the propagation of the prior through the channel. So a familiar example would be a virus self-test, right? A virus self-test takes a glob of yourself that has to do with whether you're sick or not, and then it propagates it forward to a positive or negative result. And so let's say that you get a positive result, okay? And this is kind of like your evidence, the evidence that you have received. But the problem is that you're not really interested in whether you get a positive result, right? You're interested in whether you are sick, right? But the kind of physical mechanism of the virus self-test is not going to be sufficient for this. What you want is, given that I have a positive result, whether I'm sick, not the other way around, right? So that means that you need to invoke a prior on whether you're sick. And sometimes you don't actually feel you're sick, and you get a positive result, right? And then that is going to make you think that, okay, maybe I have a false positive. But what the positive result should do, according to Bayes' rule, is to raise your prior. That you're sick or not. So let's say that you begin with a half and half, a uniform prior situation, and as long as your test, the probability of a true positive is more than a false positive, which it should be for a test, right? Your prior that you're sick would be raised, right? And likewise, if you think that COVID doesn't exist, or that you're the second coming of Christ or something, that you can never get sick, then you will never update, no matter how good the test is. You will never think that you're going to be sick. Okay, so this is Bayes' rule, and what I'll introduce next is the map that I've already talked about, is the Pets recovery map, which is seen as the kind of you can think of it as the Kleenex of quantum Bayes rules that is the most canonical in that sense. And it looks like this, okay? And one thing to note is that the gamma here is no longer a distribution of probabilistic distribution, but rather a kind of a best quantum theoretic guess encoded in a density operator. And quite quickly, you can already notice some structural similarities. The Fi and If relationship here is embedded in the adjoint taken on the forward channel. And there's a kind of a denominator term that is sandwiching between the input of the Bayes map. And then at the side, you have the kind of numerator term that kind of links up with the prior in Bayes rule. And it's even more obvious if you write it in a map theoretic decomposition of maps. That the kind of inverse term goes first, then the adjoint term, and then finally the numerator term later. Okay, So here's an expectation. Let's say that I have an actual input state that goes through a forward channel and I get an output, but I don't know what this thing is. So this is kind of like whether I'm sick or not. This is the virus self-test, and this is like my positive result, for example. Okay, and now I get I do a retrodiction. I'm asking myself, am I sick or not? And it's based on some kind of prior belief on whether I'm sick. And then I get this result, and this is my new prior in that sense. Okay, and this is really what's happening with regard to the virus self-test situation. And sometimes you don't feel sick and you get a positive result. What do? Sometimes what you do is you take another test, right? You take another test to see whether you got a false positive. And let's say that you just get another positive result, and now you update it based on the new prior that was based on the result of the previous test, and you get a new update, and you can expect what I'm going to keep doing is I'm just going to keep adding tests, and let's say you keep getting positive results. Okay. And there's some expectation that no matter how skeptical I was, as long as I wasn't completely cynical and completely pure about the fact that I'm never going to be sick ever, okay, as long as I have just a little bit of probability, as I get 1 billion positive results, that 1 billion positive COVID tests, I should converge, if I'm doing Bayesian reasoning correctly, to the fact that I'm sick. I should converge to the fact that I'm sick. Okay, and essentially this is the idea that as I keep accumulating this repeated evidence, I should essentially reach the conclusion about what was the actual input state in some sense. And this is what we are calling the asymptotic frequentist kind of feature in Bayes' rule.
Question.
Yeah.
In the classical case, it wouldn't matter if I did it the way you described, which is I get the first test, I update my prior to my posterior, and then I use that in the next step. I could instead just take my original prior and take the string of all the outcomes of all my tests, and just do a single update prior to posterior. So are you assuming the equivalence of those two techniques for the quantum case as well, or are you allowing that they could give different results?
So
you do it sequentially or all at once?
Yeah, so this is really good. So this, what you said, is the case if your evidence is pure. Yeah, so in like hard evidence, you know. So what do you mean by like essentially if you can imagine that the output over here, right, might be, you can actually update based on soft evidence, right? That it's actually a stochastic distribution rather than a pure state. And so what the relation that the kind of equivalence that you mentioned, I believe it works for the hard evidence case, but for soft evidence, actually the sequence in which you receive the thing gives you different results actually. And whether you're updating the prior on the fly as you receive, or you update it all at once after a big situation, you get different results. Yeah.
So the difference, sorry.
I think I still don't understand the difference between hard and soft. So
hard evidence would be that you get some click, for example, a positive result. There's just like a 1 and a 0, for example, in your probability distribution. A soft thing is kind of like you got a positive result, but you were drunk or something. Like you think you have a positive result and you're pretty sure, but you were inebriated or something like that. You have a soft evidence, and the weighting that you put is like a different thing. You can, it's called soft and hard evidence.
So the COVID test that you mentioned is soft evidence, but if there was a COVID test that was perfect, and that for sure is positive if you're sick, but negative if you're not sick, then that would be hard evidence.
So no, so the hard evidence and soft evidence thing is always about the output. It's not about the test itself.
So the soft evidence is something like when you do the test afterwards, the test only gives you a probability of whether you are sick.
Yeah. That basically it goes. You can imagine that what you get out of it is not a pure state. Yeah, it is some kind of distribution, stochastic distribution.
Is it like, for instance, I've had COVID tests where like positive would be 2 lines.
Yeah.
If it had 2 lines, and negative it's 1 line.
Yeah.
But sometimes I weren't even sure if there was 2 lines.
Yeah.
Or if the second line was actually a reflection from some.
Yeah, you could think about it that way.
So I could say that, well, was it positive? And then I would say, yeah, the result was 80% positive and 20% negative.
Kind of like that. Yeah.
But when we think about like most measurements that we do, like, I don't know, in quantum theory, you can measure something.
Yeah, you get a click, no?
Exactly.
Yeah. So
you're saying that most of the times that we're used to in quantum information, there is no difference between the sequential thing and the Rob mentioned.
Yeah.
Or the...
Yeah, so I think this one is worth for me to like kind of look into deeper and like really kind of pass out the different kinds of updates. This is actually a thing that me and my colleagues have been talking about. Like, when do you, like, Bayes' rule gives you the way to update, but it doesn't tell you when to update, for example, which is really the question here, right? But there is quite a lot of literature on these belief kinematic things that when you kind of go deeper into the question, a lot of the ways that you update, or you think it's equivalent to update two things, it turns out that the protocol actually matters, which is a bad thing, because you want everything to be the same when it comes to these rational decision-making stuff. Okay, but having said all that, you can kind of think of this not as even a practical thing. Like, I'm just saying that in classical Bayes' rule, we have certain properties mathematically, and a quantum Bayes' rule should recover these properties, even if it's not the practical or the canonical way of, saying, doing a update in some experiment, for example, which people disagree about. Yeah, does that help with the thing?
Yeah.
Yeah, it's honestly a little bit foggy. I think there's this one paper that is called Getting Wiser on Multi-Set Evidence. Yeah, and basically they kind of contrast these ways of updating. Like, should you update all at once, or like, sequentially, and then, yeah, depending on the kind of evidence you have, it's going to give different answers, which is not what you want in some sense, right? Okay, so but this is really mathematically, this is the structure that we're talking about, and the question is, and the point is, if this works for classical Bayes' rule, the spoiler alert is that it does, okay, we will want this for the whatever quantum Bayes' rule that we propose, for example, the PETS map. So here's the results. Here's a bunch of ongoing work. So for classical, it's basically closed already. That essentially, if your map, performing these kind of retrodiction iterative protocols on your map, is able to always reach the kind of true state that you have been throwing into the protocol. If you're always going to be doing that, no matter what prior you start with, that it kind of converges to the actual state, then it's going to be if and only if the inverse of the map exists. This is for classical.
So is there any requirement that the prior should not be trivial?
Yes. So there's a kind of embedding here that you can't start. You have to start with a prior that has like full rank. Yeah. That you can't have any zeros in that. Yeah. Good. So So the proof for this comes from a bunch of different lemmas, and we essentially use a thing called Zhang-Liu's theorem to do this. And I'll just kind of mention two particular points here, that what we call like the no epistemic harm properties of Bayes' rule. Basically, every time you receive evidence, if it's kind of this repeated evidence protocol, every time you receive it, you shouldn't be straying away from the actual state. Right? That seems that in terms of your trajectory, you shouldn't go away from the fact that you are really sick, for example. And it doesn't matter whether it's the post-processing side or the pre-processing side. In that sense, okay. So this is a bunch of things that we found that classical Bayes' rule adheres to. And so how about quantum? Okay. For quantum, we don't have an analytical proof. We don't have an analytical proof for the fact that these things are the case, in particular the asymptotic frequentism thing. But the good news is that for all the maps that we have covered, and whether they are singular or not, the non-singular one is this version. And for various kinds of dimensions, it holds so far. Okay, but as you can expect, there are certain issues, right? It turns out that at least for the PETS recovery map, this no epistemic harm thing is in fact violated. That in the trajectory of the Bayesian update, you can actually stray away from the true state as you're updating, but then eventually you converge. Yeah, okay? This was really surprising for us, and we are very disturbed by this. Okay. What's worse is that we will think that, okay, this one's violated. Maybe we can figure this out, right? But what's worse is that turns out this is violated also. And the reason why this is even worse is because we were using this for the proof upwards to the asymptotic frequentism in classical theory, right? So now we can't use this anymore because numerically this is false. You can't exploit Zhang-Will's theorem to get from here up to here.
Sorry, could
Yeah.
you
Yes.
explain the classical case a bit more?
Yes.
So the classical case, the theory is that you can have asymptotic
Frequentism.
if and only if your channel is invertible.
Yes.
What's the intuition behind that?
Because if that channel is not invertible, actually what will happen is that, let me see whether I can just show you. Okay. So you can kind of imagine a map that maps a simplex, a trait simplex to a bit simplex, for example. This is not going to be invertible, right? This is singular, right? And you can imagine that this entire edge goes to one point, okay, in the image, right? Then what's going to happen is that, okay, then let's say that my prior is here, right? And I do this updates on this evidence. And what Bayes' rule will do is that it will kind of like move closer and closer, and it will eventually stop here. And if you started here, what will happen is that you move and you will stop here. No, our prior matters, right? But the point is that this is not that surprising because it's not that surprising because the solution space was not identifiable. It all got squished and all the information is gone. Yeah. So yes, asymptotic frequentism is a property of invertible channels in that sense. Yeah. Okay? All right. Yeah. There are some open questions with regard to what I just said that will be nice to talk about, but yeah. So yes. Okay. So all this to say that we can't use an argument analogous to the classical one to prove asymptotic frequentism. I know that what I just said is really anticlimactic. It's basically I'm just saying that what we tried doesn't work. And yes.
In the
Yeah.
case, those bottom two things didn't hold. That's
Yeah.
analytically.
It's numerically proved. Yeah.
Examples.
Sorry?
It's numerically found counterexamples to.
Yes. Yeah. And once you find one, then it's over, right? Like yeah.
Are those counterexamples intuitive? Like you have simple counterexamples where you sort of understand?
Not really. Okay, but there is a sense that there's some intuition is that for the pre-processing one, this guy, it tends, so far we have found that it happens for singular channels. Yeah, which makes some sense, right? But the thing is that, a singular channel is a non-invertible channel. For example, a completely dephasing channel, right? It just strings your whole block sphere to a bit, right? Like a line, no? And in these cases, we found that this can happen, but we have no geometric intuition for that. Yeah.
In the classical case, when you have a non-invertible channel,
Yeah.
those bottom two conditions help because your quantum counterexample
Yeah.
is a non-invertible channel.
Yeah. Yes.
Surprised that they continue to hold even for non-invertible channels classically.
So this one, it shouldn't be surprising because after this, it gets propagated through the channel, right?
Okay.
So this
What is not surprising?
this particular one, this one, it may not actually be sensible to even apply this for singular channels in a classical situation, depending on the scenario.
Then it feels like it's not a contrast between quantum and classical, because if you went to the classical case and said, what about non-invertible channels? You would again say, no, it doesn't hold. So it's sort of like, the classical and quantum cases are similar in that regard. Yeah?
Okay. What I was saying before is that it occurs, the closest thing to an intuitive case is the singular channels, but this also occurs for non-singular channels in the classical case, the invertible channels. Yeah.
Sorry, classically, those two inequality, they hold for both singular and non-singular channel. Is it a statement? And
It sounded like you just said that the second one need not hold for non-invertible channels, even classically. In which case, there's a caveat to those check marks.
I think the okay, I'll need to check back because I haven't been thinking about this that much recently. But I got a feeling that for certain singular channels, as in for singular channels, this statement may not be well defined. Yeah, so I might, yes, it might be a bunch of caveats down the line that I need to check again. Yeah, but thank you for asking. Yeah.
It sounds like potentially it's good news because your principle was like everything that holds classically should hold quantumly. It turns out that the only quantum failures are for singular channels, and classically, it's also the case that the only failures are for singular channels. Then you're back to everything that holds classically holds quantumly as well.
Okay, all I know is that I remember numerically that I was disappointed. Yeah, so but okay, before I answer Marina, the point is that for the singular channels and non-singular channels for classical, this holds, and it doesn't hold for the quantum case, right? And this is the post-processing thing. So the singularity doesn't matter because it has already been placed through the channel's image, right? So this is well defined for both singular and non-singular channels, and classically this holds, but quantumly it does not. Yeah.
And your quantum counterexamples here as well involve singular channels?
No, it's for every channel. Like even non-singular channels. Like we were just sampling randomly. It wasn't like a measure zero situation. Yeah. And we were just sampling randomly and we will find these situations. Yeah. Which also suggests that they are quite common, right? Because we were sampling randomly and we still found them. Yeah. So it's this was really disappointing. But we didn't find it for qubit channels though. We found it higher in the higher space. So I don't know whether there's some reason for why that is. Yeah. Okay, sorry.
Sorry, can you can you explain again what does address no epistemic harm means?
So essentially it means that as you keep receiving like these positive results for your virus self-test, your quantum virus self-test or whatever, right? You shouldn't, as you're kind of going through your Bayesian journey, you should always go closer to the fact, informationally closer to the fact that you're sick.
But what if you have those,
as
you're saying, like what if you do one test and then you get the negative result, but it's because that one test was wrong? That'll take you far away from, but it's not.
Yeah, so in this situation, what we're doing is always with respect to the same, the evidence is always the same distribution. Yeah, and that can be hard or soft evidence. Yeah, so it's not going to be a situation whereby it kind of ping and pongs like between a positive and negative result. Yes, you're always getting positive.
And then your reasoning has to be such that you're always more sure.
Yeah. So as you can tell, this is not really like quote unquote a practical example, but it is just a property mathematically that it happens in the classical side. We will want it to happen also in the quantum side of things. Okay, so let me just go through this very quickly. So these continuities between classical and quantum may be for different reasons. It might be that we're using the wrong information measure. We shouldn't be using these Umagaki divergences. But we tried it for Bour's distance, fidelity, and trace distance, and we still get these violations. Yeah. There might be some other quantum-based rule that fulfills all these things that the classical thing does. Or it could be the I give up option, which is that the quantum theory is simply a different information geometry.
Sorry.
Yeah.
In classical case, this D is
Yeah.
distance you use the several different measures, and then you always hold constantly. You try different measures, and this you always can find some counterexamples to this.
Yes. Yeah. Yep. So fortunately, asymptotic frequentism, the one that we really want, still holds in our numerical searches, but in any case, there's still more work to be done. Let me just go through this thing very quickly. Okay, so this is classical. It's basically these Bayesian trajectories for a trig channel. Let me see whether, can't do that. Okay, I don't know whether you can see this. Oh. So what you have down here is this the kind of a true state that you're feeding into the protocol. And this is the evidence that you're updating on. And each of these trajectories begin quite close to a facet, is some prior. And you can kind of see them go down as they update and go towards the true state here. Okay? So one of the features that you immediately kind of notice is that. Oh.
So what do you mean by the evidence?
It's the post-processing thing. For example, your positive result, right? So it's this whether you're sick is post-processed through the channel, and then you get some result. And what you notice is that there are all these kind of like weird parts that the Bayesian trajectory almost like takes a sharp turn, and then once it takes a sharp turn, yeah, sorry,
Understanding the
yes,
phi p.
Sorry. So phi, this is like a notation difference. It's what I denoted as E. It's your stochastic matrix.
So you have two triangles. Phi
Yeah.
p lives in the smaller triangle.
This is the image of the channel.
Okay.
Yeah. So the simplex gets mapped down to this this image down here. Yeah. And you can kind of see that as the base updates occur, and then it goes eventually to the true state, which is the asymptotic frequentism thing. But there are all these like little like highways that they are traffic jams in some sense, right? So how do we understand these traffic jams? One way you can kind of think of it is probably more obvious in the parts where the traffic jams look very linear. And you can kind of ask yourself, what is the shortest line that goes through the evidence that touches the facets of the simplex? Okay, and in this case, it will be this particular line here. And if you kind of like invert it out, you find that it's exactly these traffic jam areas. Okay, basically this, and for this case, it's the same thing. Okay, and sorry, the basic case, nope, go back. The basic idea is that this is the region that was most squished by the image. Basically, the states get the most indistinguishable here, and basically Bayes' rule is able to be robust to the fact that, okay, at this point we need to be really conservative and be much slower here. Okay, and this is just the kind of trajectory properties that emerge from this thing. Okay, you can also ask me about some other trajectories with regard to the quantum case, especially with respect to something that is uniquely quantum. On this particular update channel called the extended prior patch map. But yeah, this one, if you're interested, you can ask me about it. It's about extending your prior and using a prior on a bigger space than you need. Okay, but the closing remark for this aside is that it is natural to ask whether these trajectories are kind of a geodesic that is balancing between the push of the inverse, because as we are kind of seeing here is that Bayes' rule knows where it should go, right? When the inverse exists, right? But at the same time, it's not letting go of the fact that maybe it's a false positive. We shouldn't let go of the fact of our background information that maybe this disease is very, very, very rare, right? Okay, and so therefore it's kind of a push and pull between the inverse and the prior in that sense. Okay, but this is something that I don't know how to formulate, but this is interesting to consider. Okay, let me just close this part. So classical Bayes washes out the prior in the long run when evidence is received consistently. We should expect this for the quantum Bayes rule, but the road has been a little bit frustrating because of the geometries that we have. Okay, and so this is where I say help wanted in a sense. Yeah.
Is it possible that this is sort of an artifact of your distance measure?
Yeah, so it's definitely possible. In fact, I think this is the most likely situation. But we have tried the kind of the big distance measures. So it might be that it's a really special distance measure, right? And if that's the case, then we will know what the patch map is really doing, right? In that sense, right? Okay, yeah. So that's iterating the prior. Now we're going to talk about doing the opposite of that. We're going to call it hacking Bayes. And I'll just kind of wrap up this part. I mean, I'll talk about this part, and then after that we'll wrap up. Okay. So let's say you have a guy that has an initial belief on some state space omega. For example, let's say that he thinks that it's likely that my concert tickets are selling well, doing well. But he encounters his manager, and his manager tells him that you should consider, our sales team says that we should consider lowering our ticket prices. So in some sense, he encounters evidence that is not compatible to his initial belief in that sense. Okay. So there's two things that he can do, right? One thing he can do is he can do the genuine Bayesian update, that he updates his initial belief, here written as gamma g, like a genuine prior, and he updates it to a genuine conclusion PG, okay, which is what solves this equation here, okay. So this is the proper way to do it, okay. But as you can imagine, there's another thing that he can do, okay. He can do an evil thing, epistemically evil thing, okay. And instead, he now considers his initial belief as PH, okay, same belief, okay. But now it's his conclusion, okay. And he basically holds on to his initial belief, and because his manager is a Bayesian and is going to check whether they did a Bayesian update, he's going to come up with a prior that arrives at his initial belief, okay? And for example, he could say that, oh, secretly I have some ticket sales that no one knows about yet, okay? So we call this prior hacking. Essentially, instead of that given a prior, you arrive at a conclusion, you instead hold on to a conclusion you want and come up with a prior, okay? So while genuine Bayesian update, a prior induces the conclusion, for prior hacking, a pre-selected conclusion induces a hacking prior, okay? So in some sense, you can think of it as the perverse or reverse engineering of retrodiction, that you kind of go backwards instead of forwards. You come up with a prior that will arrive you at the conclusion you want, okay? And so this was just honestly a morbid curiosity I had about like whether you can always do this or how often you can do this. And so how often is prior hacking possible? Okay, and formally it's given some forward channel E and some conclusion P and some evidence Q, when and how can we obtain a prior gamma that solves that equation? Okay, and to do this, you can do some massaging of the equation. I kind of write it as a decomposition of maps as per Bayes' rule, and introducing element-wise divides and products, you can write it as this. Okay, and finally, you can write it as a subject like with gamma here, but notice that gamma also appears here. Okay, so this would be what defines your hacking prior in that sense. Okay, and it turns out that you can solve this thing by using a method called the syncon problem. I don't know whether you guys have heard of this thing, but it's a kind of a matrix scaling problem that essentially if your channel, if your matrices fulfill certain properties, then you can use this thing to find the object that solves that matrix equation. Okay, and essentially you start with some object here, and then you feed it out there, and then you just keep going it over and over again, and eventually it will solve the equation that you want. Okay, and in our paper, we kind of explain what are the exact conditions for prior hacking and how to algorithmically obtain the hacking prior. Okay, but this is not that evocative. Okay, just take note that you can, this algorithm, you can kind of write it as two couple equations like this. This is not very evocative. Probably the more evocative way to put it is given for what forward channel, E, can I always prior hack for any conclusion and any evidence? Basically, any conclusion I want and every evidence I receive, I can seem like I'm a perfect Bayesian. I'm doing Bayesian reasoning, but actually I'm not changing my mind. I'm actually doing the really pathological thing. What forward channels can I always do this? And it turns out it's the vast majority of channels. Okay, as long as your stochastic matrix doesn't have zeros in it, you can do it. Yeah. As long as your stochastic matrix doesn't have any zeros, you can always prior hack regardless of the conclusion and the evidence that you want. Yeah, so this is really the thing here. And when we upgrade to quantum with regard to the Pets recovery map, we get very similar results. Okay, and you can kind of consult the paper, but The way that this is done is very similar. It's just kind of upgrading from matrices to operators. And just to take note is that with regard to for the quantum channels, you can always quantum hack any channel with regard to any evidence or any conclusion, quantum theoretic conclusion or evidence, as long as your whatever input state you put in, it comes out as a full rank state. If that's the case, then you can always prior hack, right? Okay, so this is just how this research kind of started, okay, that we obtained the exact conditions and proofs for prior hacking. And the key resource for these things was this synchron iteration problem. But then we began to ask the question of like, where else has synchron iterations come up? Okay.
You mentioned that the quantum case, as long as it is always full rank output, then it is fine. That's not the same condition as singular channel that you mentioned before, right? It's a different condition.
Yeah, it's a different condition. Yeah. So it's more general than that. Yeah. Okay. So and it turns out it comes from this thing called Schrödinger bridges. Who has heard of Schrödinger bridges? Yeah. Okay. So neither did we. Yeah. Okay. No idea what this is, and it's the same Schrödinger. Yeah. But it's not has nothing to do with Schrödinger equation. It's not quantum. In fact, it comes in transport physics. Okay. It's like in optimal transport and stuff like that. Okay. So what are these Schrödinger bridges? Okay. So Schrödinger basically come up with this question of like, okay, let's say that I have some kind of model of some dynamics E, some Brownian motion, for example, and I prepare a state P and it goes through E, and what I find is that it outputs Q. I take a lot of data and outputs Q. But what I find is that it turns out that Q is not E on P. So what I know is that my model of the dynamics is definitely wrong, right? Okay. So what do? Well, now I want to update my process to a new process that I call F that propagates P to Q. Okay. But at the same time, having said that, there were a bunch of PhD students that came out with this model. So I don't want to throw it away. They put in effort into this thing. I don't want to throw this original model of dynamics away. So what I do is that I make sure that whatever I come up with here is like informationally closest to the one here. Like it's informationally the closest object to the dynamics that would have occurred over here at this side, okay? And so you can kind of think of it as kind of minimum change from the original dynamics that satisfies my empirical observations. But I don't just account for the observations, but I also account for the reference information that I originally had, okay? So once I said it this way, this sounds a bit like Bayes' rule, right? Okay, but let's just keep going, okay? So this object that you get at the end of it, this F object, but you get the joint object that is F on P, okay? This thing that we're denoting as BYX is what is called a Schrödinger bridge, okay? But of course, since the problem is defined by this, it's actually one-to-one with the dynamics, the conditional probability object as well. And it turns out that the Schrödinger bridge problem, to get the object that satisfies this thing, is done using a synchron iteration method, okay? And in particular, it's a synchron iteration method with these potentials that you kind of just update these things through a couple equation, and the couple equation is this, okay? And if you have forgotten, these couple equations is exactly the couple equations for prior hacking, okay? So then I just want to let you know that when we were looking at these papers, none of this was obvious because the transport physics notation is very different. Their goals are very different. The way that they write probability distributions is very weird, right? But we kept staring at it and there were a lot of things that were very similar and we were thinking like, okay, what's going on, right? And so we kind of massaged the thing and we realized that you can write a Schrödinger bridge in this way, right? And if I show you what Bayes' rule looks like, then you'll notice that there's something really similar going on. It's quite evocative, right? Okay, so then what's happening? Okay, so let's unfold this, okay? So you write it as a decomposition of maps, your Bayes' rule, and you can write your Schrödinger bridge as a decomposition of maps as well, okay? But remember that your Schrödinger bridge, unlike Bayes' rule, is a forward channel, right? It's not a reverse channel, right? It's a forward channel because you're updating your forward dynamics, okay? So then what do we do? Well, what we tried is we took the retrodiction on the Schrödinger bridge, okay? And we did it on P, okay? In prior hacking, this will be your conclusion, okay? And then after some massaging, you find that it's exactly the prior hacked base map, okay? And some of you might think like, okay, Clive, I noticed the similarities, but what does this connection mean? What this connection means is that we have explained why Schrödinger bridges work in optimal transport. It's because Schrödinger bridges is when you don't want to update your initial state, but instead you do a base update, quote unquote, on the process, right? You're not going to change your mind about what happened in the past. What you do instead is is the base dual of this, that you update it on the process instead. So one example that I can give you is like, okay, imagine I'm a teen, I'm going to a party, right? Okay, and my crush is there, the girl I like is there, right? And I have this channel in my head that like, if the girl smiles at me, it's more likely that she likes me, and the girl doesn't smile at me, then it's less likely that she likes me. Okay, and I go there and I'm with Nick. Okay, and Nick is a really, really Bayesian, so he knows what's the rational thing, right? So I go there and I see the girl, and the girl doesn't smile at me, right? And I'm very sad, right? And then Nick comes up to me and says like, okay, so you need to do a base update now, right? And what I can do is I can do two things. I can do three things actually. One of them is I just say that, yeah, she doesn't like me, right? I can do that. The other two things I can do is I can just gaslight myself and I can gaslight Nick as well, right? I can tell Nick that like, oh, but there was this other time that, she said this thing to me and like, so I think it's still 50-50, which is prior hacking, right? I invoke some unknown evidence in the past and I arrive at the same conclusion I started with. Or I can do Schrödinger bridges. I can tell Nick that, no, when a girl doesn't smile at you, actually that means that she likes you. I can change my model of the dynamics, okay? And it turns out that what this theorem proves is that with regard to the Bayes inverse, this Bayesian character of these things are the same, yeah, okay? Of course, Schrödinger bridges is not pathological, like I said, because P and Q are observations, right? But what it shows is that Schrödinger bridges are Bayesian updates on the process rather than the initial state, which is what Bayes' rule normally does. Okay?
What do you mean that those things are the same?
So it means that they are like conceptually parallel. Like for genuine Bayes update, what you do is you kind of update on the initial state, right? That you see the evidence, you update on the initial state. But what Schrödinger bridges does, which is a lot like prior hacking, is that no, I'm not going to update on my initial state because I'm sure that my initial state is correct, right? For example, I observed this or I prepared the state, right? And then, so what is the most Bayesian thing to do then? You can't update on the initial state now, right? So instead, what this theorem shows is that you update on the process. And the Schrödinger bridge is exactly this thing. There's another paper that came out by some of my colleagues. It's called I think it's called the patch transpose and the minimum change principle. What you will find is that the minimization problem for the Schrödinger bridge looks like a lot like this minimum change principle. That essentially you're trying to keep the joint states as close as you want together. Yeah.
In the usual base updating, as you mentioned earlier, my initial belief is pure, then I cannot update my belief. But for the Schrödinger bridge, even if my initial belief is pure, I can still update the channel.
Yes, you can do that, yeah. So, yeah.
Even if your initial channel is pure, meaning that the channel is a deterministic function from X to Y.
Yeah, you can also still update it. Yeah. So you can kind of think of it as like after the observation, there's a constraint space in like the channel space. And what you do is you take an I projection, information projection of what you originally wanted, and you project it onto that solution space. Yeah, that's really what the Schrödinger bridge is doing. And so you can do it from even a really, really bijective channel, for example, or a very pure channel, yeah.
Given that fact, it doesn't feel so much like Bayesian updating anymore. Because if I say, I'm certain about the value of Y for every value of X, and then I get new information, and I change my mind now.
Yeah.
that's not sort of updating. It's really sort of overthrowing my own beliefs.
So,
Whereas if
yeah.
you're doing it like Bayesian updating about X, you never, like if you ever assign anything zero probability, you would never overturn those beliefs. So it feels, in that regard, to be very different from updating.
Yeah, so the Bayesian part of that thing would be really the fact that you don't give up the prior in that sense. The prior is in some part of your channel space, right? And you will still take note of that channel and you go to the closest thing in the constraint space, like that. It is interesting of what you're saying about like when is the case that we don't update the prior at all in a genuine Bayes update, which would be the situation of like your pure scenario, right? And it turns out that this has to do with this other thing that we are calling aggregate Schrödinger bridges that I'll mention just in passing later. But there are like parallels to this in that level because actually Schrödinger bridges, you can kind of think of it as like just updating on the entry level rather than the entire space. I'll get into that later, or we can have more discussions as we go along. It's quite complicated, yeah. Okay, let me just go through this very quickly. So yeah, how about quantum, okay? Because what we just taught was all classical, right? For the classical Schrödinger bridge, we solve an optimization problem, which then is solved by a matrix scaling problem. But for quantum Schrödinger bridges in the literature, this mathematical physics literature, we don't have an optimization problem, okay? What they instead do is they essentially kind of construct essentially by eyeballing the classical Schrödinger bridge situation, and they upgrade things to operators, and they say that this needs to fulfill certain rules, and they say that okay, these are probably where the quantum Schrödinger bridge will live in, but no one has a canonical choice for these quantum Schrödinger bridges because it's essentially constructed, right? So we have some ambiguity. Okay, but now that we have this kind of dual-like relationship between bridging Schrödinger bridges and Bayes, could we use this particular relationship to kind of like induce a quantum Schrödinger bridge? And the answer is yes, you can, right? And in fact, once you kind of force this commutativity diagram to hold in the quantum regime with regard to the PETS recovery map, it turns out it picks out exactly one quantum Schrödinger bridge in the family of candidates right now, okay? And we call this the inference consistent QSB, quantum Schrödinger bridge. And it has certain properties that makes it kind of evocative of the classical Schrödinger bridge. I won't go into it very deeply, but what we are saying is that the PETS map is equipped with a quantum Schrödinger bridge dual in that sense. Okay, so just two quick asides before I close and wrap up. So we have already talked about how you can iterate Bayes rule and kind of keep updating Bayes rule, right, over repeated evidence. A question that we asked quite immediately was, can I iterate prior hacking? Okay, that's such that instead of going forward in the Bayesian trajectories, I go backwards in that sense, right? I prior hack over and over again. Basically, I don't want to face the truth, I go backwards. Then this is my new thing that I will not give up, and then I don't want to face the truth, and I keep going backwards, and I keep stepping backwards and doing prior hacking. And it turns out that this sends your prior to become increasingly pure and eventually approaching a pure state. Okay, and of course we call it radicalization because essentially you're just gaslighting yourself over and over again. And what's interesting is that in these simplexes, what this means is that there are certain regions that all go to the same pure state and other pure states. And of course we call these lines that separate the regions party lines, right? Okay, because we had to. But yeah, what we're saying is that it kind of it invokes certain intuitions about what we think would happen if you keep prior hacking. Okay, and the last thing that I will say is that with regard to Bayes rule, we have asymptotic frequentism with regard to states, right? One thing you might want to ask is that if Schrödinger bridges are, in fact, Bayes rule updates on the process, shouldn't we expect asymptotic frequentism with regard to Schrödinger bridges, right? That over time, as I iterate Schrödinger bridges, I should approach some true dynamics, right? And what this means is that if this is the case, then you can use this for channel tomography, right? You can use these quantum Schrödinger bridges in some iterative way towards channel tomography. And the answer is yes. Okay, you can do this for classical quantum. Okay, but there is some interesting twist. You need to aggregate them in a certain way. Okay, so if you're interested, we can talk about it. Okay, so let me just close this part. So we talked about prior hacking. In the paper, you will find the existence theorems and algorithms, both for classical and quantum. It's all analytical. And Schrödinger bridges comes from transport physics, but one of the main contributions of this paper was to show that essentially these two, that Schrödinger bridging is essentially what you do if you're not going to give up your initial state because maybe you prepared it or whatever for any reason, but instead you update the process instead. And when you extend it to the quantum regime, you obtain a unique inference consistent quantum Schrödinger bridge. Okay. Yeah, so the basic idea is that proposals for quantum-based rules should have some kind of corresponding Schrödinger bridge recipe as well. Okay, so that's really what we're talking about. The two new features that proposals for a quantum-based rule should account for this asymptotic frequentism thing and the fact that we should have a process dual in a sense. Okay, so future work, just to close. It would be nice to finally get all the analytical proofs for the numerical results, in particular, the asymptotic frequentism with regard to the PETS map, comparing with maps besides the PETS map, and of course, to get the minimization problem for quantum Schrödinger bridges would be great. And I already mentioned these trajectories and whether we can understand them as geodesics. And finally, this idea that we can use iterated Schrödinger bridges, quantum Schrödinger bridges for channel tomography, which is what we're working on right now. Yeah, and thank you for your time. These are my collaborators. How are we doing on time? Is it okay? Okay.
Not too bad.
Okay.
Any questions?
This idea of updating the process rather than the initial prior is somehow very natural if you just think about processes themselves being consisting of probabilities for stuff happening.
Yeah.
So it seems entirely natural.
Yeah.
Could you imagine something that was somehow in between, that you
yeah.
decide how much you want to update your
yeah.
initial prior, how much you want to update your process and parameterize that, and then you could do some mixture of both of those?
Yeah, I think that's a really interesting possibility. Yeah, I mean, I haven't tried that, but that sounds almost like a mixture between a genuine base update and like your Schrödinger bridge update, no? Yeah, yeah. That's nice.
Have you thought at all about the relationship of this to the Diffinettian approach? So, if I'm flipping a number of coins,
yeah,
then one way, and maybe I don't know what bias the coin is.
Yeah.
One way to formalize the problem, how should I update my beliefs about the bias of the coin, is to do it as follows. Like rather than just saying I have some prior that it's say an unbiased coin, and then I change that prior to posterior. What you instead do is I start with the prior over biases.
Yeah.
Maybe it's a fair coin, maybe it's this kind of coin.
Yeah.
And then the Diffinetti form is something like, okay, you have a prior distribution over all possible biases, and then n coin flips are just governed by whatever that bias is. So what I'm certain of is that they all have the same bias.
Yes.
So
it's like the parameter, right? Like you're updating on the parameter of the bias.
Right.
Yeah,
So
yeah.
then I do some coin flips, and what happens is that distribution over possible biases starts getting narrower and narrower, and I can never increase the weight of any bias that I assign initially zero probability to. But that in that case, any two agents who have different priors over biases perfectly converge to distribution of the same bias in the limit, and that's very different. Distribution over biases is very different from just like a single distribution of heads and tails.
Yeah.
So I was trying to kind of see how what you were talking about relates to that. I guess if it's some fact in the world, like whether I'm sick or not, that's a bit unlike the bias.
Mm-hmm.
So maybe that's why we don't do it in the Diffinettian way. But yeah, have you thought about that alternative way?
So actually, this is like the current obsession of one of my colleagues. Like he wants to kind of unite these two approaches. And I think he's actually coming up with some kind of formalism to do retrodiction in a way that is really very Definitian. That you essentially don't have, it's not that, like inside your many copies of like in every box you think that it's either a banana or an apple or something, right? But if you have many copies of this thing, maybe should you think of it as like many copies of boxes with either bananas or apples, or many copies of all bananas and all apples, for example, right? It's how do you kind of reconcile retrodiction in one situation and in the other, right? And I think he's currently working on these things. And so we're in talks about it. I'll just be very frank, I don't really understand it very much, but I think if you're really interested in this thing, I think my colleague will be coming to PI in August, like even before that. Yeah, Mingxuan. Yeah. So Mingxuan is actually looking at this Definity thing right now. Yeah.
So he's going to the Toronto conference and he has asked me to maybe also have a present.
Yeah. So yeah, even before that we can talk as well. Yeah. Because I think his findings is very interesting, but I'm still interfacing with it. Yeah.
The other topic I'm reminded of is from the stuff at the end regarding Schrödinger bridges is so Ariel Tisha and his co-authors have this sort of entropy-based approach. So they're kind of working in the framework of Jaynes and his max entropy principle. So max entropy is a way of sort of picking a prior when you have certain constraints.
Yeah.
So you can think of it this way, that like let's say I have some old prior P, and then I learn some new constraints.
Yeah.
There might be many distributions that are consistent with that constraint. And the idea is something like, okay, of all those distributions that are consistent with the constraint you found, choose the one that means that you've learned as little as possible relative to what you knew before. So the relative entropy, for all these distributions, find the relative entropy to your old prior.
Yeah.
Choose the one that makes that relative entropy as small as possible. Because it basically is sort of as conservative as possible.
Yeah.
As little as possible. So in some sense, I choose the distributions that as close as possible to my old beliefs.
So it's max cent, but for relative entropies.
Yeah.
Is that correct?
Yeah, exactly. And I guess it's minimum relative entropy.
Oh, yeah.
I've learned as little as possible. So
Okay.
I'm still as ignorant as can be relative to this new thing I've learned. So it's still being, like max cent is a sort of conservatism that says I should know as little as possible relative to this data. And this principle is like that as well. That
that's nice.
As little as possible for this
Okay.
data.
Okay.
And it felt to me like your description of Schrödinger bridges is a bit like that.
Yeah.
It sort of says, assume that relative to your old conditional, the new conditional you adopt should be kind of as close as possible.
Yeah.
Have I got that right?
Yeah. It is, but it's with respect to, it's the closest joint probability distribution.
Right.
Yeah, but of course the joint probability distribution gives you the conditional. Yeah. But okay. I think this is quite interesting. Wait, what was the author again?
Katisha and Griffin.
Okay. That's interesting.
6. And they show that that principle can kind of recover the Maxent principle and Bayes' rule of special cases.
Okay.
So they argue that it's sort of a deeper principle that subsumes these other principles.
This might be really related to the minimum change principle that that my colleagues came up with, and I'm not sure whether they are aware of this thing. Yeah, so I'll definitely look that up and cross-check. Yeah, that's nice. Yeah.
Any other questions?
So you start. You start by saying that like if you compare different possibilities for maps, like the PET map with the full parsic map.
Yeah.
The PET map satisfies more expectations as a Bayes rule. And then you said that like the asymptotic frequentism and this existence
Yeah.
of the dual.
Yeah.
So if I understand, is it fair to say that the one you proved analytically is that it satisfies the existence of the dual?
Yes.
I
Yes.
see. But
Yeah.
for the case of asymptotic,
No, we still don't have that.
Okay.
Yeah. And
sorry,
Ye-
the question is just if you
yeah.
take the other one, like if you take the full par sigma, do you know it does not satisfy the?
So it does. So for all the ones we checked, but I think we were more thorough with the pets. The full passing out map does have asymptotic frequentism for the ones we checked. Yeah. So, but with a big but is that the full passing out map is not CP. Yeah. So you have to always, after you get the state, you have to kind of like make it positive before you make the thing. But if you keep doing that, yes, in fact, you do converge to the thing. You basically normalize it and stuff like that. Yeah. So whether that's satisfying, I'm not sure. Whether I wouldn't call that satisfying. Yeah. So because the map itself doesn't converge, it's more of that after some post processing of the thing, it does converge. And of course, we don't have the Schrödinger bridge for this particular object either. Yeah. Yep.
Any other questions? All right, let's wrap up then. Thank you.
Okay, thanks.